Let me take you on a journey to the coldest place on Earth and its last and greatest wilderness, on a voyage to Antarctica. Hello and welcome to A Voyage to Antarctica, brought to you by the UK Antarctic Heritage Trust. I'm your host, Alok Jha. This week, my guest is the leading climate scientist, Dr Tamsin Edwards. Tamsin specialises in understanding how confident we are in climate predictions, in particular predictions of how ice melting from glaciers and the Greenland and Antarctic ice sheets will contribute to rising sea levels around the world. Tamsin regularly provides advice on climate science to the public, to policymakers, the media, businesses and charities. She was a lead author of the 6th assessment report from the Intergovernmental Panel on Climate Change, which was published in 2021. In 2023, Tamsin will be the first parliamentary thematic research lead for climate and environment, a role that's based on the concept of chief scientific advisors, responsible for bringing about a step change in the way climate research feeds into Parliament's scrutiny, legislation and debate. Tamsin is an award-winning science communicator, including through her blog for the Public Library of Science, articles for The Guardian and co-presenting the BBC Radio 4 series 39 Ways to Save the Planet. She recently wrote an essay about the consequences of rising temperatures worldwide and how to stop them for Greta Thunberg's The Climate Book. Tamsin, climate scientists are in the news all the time now for good reasons, and I just wonder if you could explain what a climate scientist actually does.
It's a great question because I had no idea until I became one, basically. I think part of the thing is that it's an incredibly broad term. The people that study the planet, it's so complex, so big, so varied. They can do it in an incredible number of ways. The thing that I do is climate modelling, which again is something I hadn't really thought about before I started doing it, pretty much. So I use computer models and I particularly work with other people that use computer models to try and make predictions about the future. And my particular interest, my speciality is trying to work out what our error bars are about the future. What are our uncertainties? How confident are we in the predictions? You know, we don't normally come up with just one number for the future. We normally try and come up with a range. Everything in science has an uncertainty associated with it. But trying to estimate what your uncertainty is for a computer model is pretty different from something in the lab or out in the field. You know, climate scientists that study the oceans or, you know, they study something in a lab, they can measure something lots of times to see how constant the values are. But with computer models, it's different. You're not measuring the real world, you're simulating it. So how do you, it's almost a philosophical question, I think, about how confident we are. Have we explored all the possibilities? Have we ruled out things we think aren't going to happen?
Now, you've kind of answered this question already, but let me ask it anyway. Is climate science, is modelling what you always wanted to do? You've just told me that you didn't know about these things before, really, but there must have been a sense of the topic or area or discipline that drove you into this area in the first place.
I had two loves as a kid, animals and playing the piano, and I sort of varied back and forth between those two things. My mum's a pianist, professional. So animal programs, you know, obviously David Attenborough, but also Chris Packham's, you know, in the Really Wild Show was my era. They really got me into thinking about helping nature, to preserve these lovely, you know, pandas or fish or whatever else. And so I got quite into the environment, and I remember being very struck as a kid at primary school. Someone came and gave us a talk about the hole in the ozone layer and the idea that humans had created what sounded like this kind of terrifically scary hole in the sky, which was letting in dangerous sunbeams, basically. I mean, he was a scientist. He was very sort of straightforward in the way he told it, but just the facts of it, you know, in the late 80s were quite shocking. And so I kind of kept that in mind, I guess. I just sort of developed a lot more interest in the environment and the natural world. Through my teenage years, I wanted to go and preserve the rainforest. It was all those kind of environmental things, particularly of the time, save the Amazon, save the whale. But then I sort of slightly got sidetracked by physics. I fell in love with physics I read Stephen Hawking's Brief History of Time because my cousin had read it or read parts of it and gave it to me for Christmas.
Did you really read it though? Because everyone says they've read that book and then they haven't actually finished it.
Do you know what? I read it incredibly carefully. I sort of pored over every sentence and I really tried to imagine all these things around black holes expanding and, you know, the ordering of the arrow of time. And I got to the end and I think I'd understood, this was age about 15, I'd understood every chapter apart from the last one, which was on string theory. And I hadn't been studying physics at school. I hadn't done it for GCSE. I'd given it up thinking I didn't like it. And then I thought, oh, I can understand this book that everyone else says is impossible. Maybe I should do this. Yeah. And I got really interested in all that kind of quantum mechanics and astrophysics and all the big picture, again, philosophical side of physics. Went and did a physics degree, went and did a PhD in particle physics.
The climate is a very complicated system of weather and water and atoms moving around the atmosphere and sunlight falling onto the earth and incredibly complicated, mathematical in many senses. So physics is obviously a really important part of it. Was the physics of the atmosphere the way you got into it, or was there something else that sort of allowed you to sort of look at climate from a more mathematical, numerical way?
No, I didn't really pick up on atmospheric physics or climate change at all during university that I remember. I still was kind of wrapped up in the very tiny, the particle physics, or to some extent still the very big, the astrophysics, the sort of universal, the galactical. But I think there's a bit of a link though in that I was really loving the big concepts and the big ideas. I wasn't necessarily, I did a lot of the mathematical modules. I chose the ones that sort of followed the theoretical physics and maths kind of options. I've always liked maths as a kid through to now. But I think it was the trying to sort of get your head around these exciting ideas of how do we know things? How can we possibly know about such tiny things as, the subatomic level? How can we possibly know about galaxies far away or how the universe evolved in the first few milliseconds, nanoseconds? And for me, probably something about what I do in climate science, thinking about it now, is kind of related to that. How can we know what the climate's going to look like in 100 years? We know how difficult weather predictions are, if we go past the next few days or even, a day or two. How can we know that when we have kind of fairly limited data to test the computer models, when it's so far into the future, we're trying to imagine what humans will do as well. I think I'm really interested in the idea of how we know things, and that probably draws together those themes.
Well, let's talk about how you know things in your field. One of the first times I came across your work was in your blog, All Models Are Wrong. And it was a striking statement to make for a modeler. And I think, you make models about the world and you decided to write a blog called All Models Are Wrong. Just give me some context for the name of the blog and why you're undercutting your own achievements and achievements of your field.
Well, on the one hand, it was meant to be quite cheeky and it was meant to sort of draw people in sort of thinking, oh, what's this about? Why are you sort of apparently undermining yourself? And in particular, at the time, I was really interested in drawing in people who were skeptical about climate change and climate science and climate modelling. So it was a way of sort of inviting that conversation. So on the one hand, it was meant to be a bit cheeky and a bit kind of provocative. But on the other hand, it's actually a very commonly used phrase. It's half of a phrase by a statistician, so someone who's using mathematical models rather than computer models of the kind that I use now, called George Box, who said, all models are wrong, but some are useful. And that phrase is absolutely the heart of what I do, because almost the definition of a model of any kind is that it's a simplification, it's a representation, it's an abstraction of something. That's true of a wooden model of something. It's true of an architectural model. It's true of a computer model, a mathematical model. They are all, in some sense, representing something in a simpler way than the real world. Otherwise, they would be the real world. So they're all wrong in the sense that they all have things that are simplified or in some sense missing from that, some details. But that doesn't mean that they're not useful to understand the world. You can do a lot with that. And as long as you are really aware of their limitations, what they can do and what they can't, where the errors might be, where they might be getting things right or wrong, and you do your best to test where they get things right or wrong, then they're useful. And that ranges from the most sophisticated state-of-the-art climate models that are thousands and thousands of lines of computer code, and they take months to run on supercomputers, immensely complex things, right down to, one single mathematical equation or line of code that can do something very simple. It can still be a useful model of something. And you change the inputs to that model and see what happens to the outputs. You predict something by changing something, almost like your own mini laboratory, but in the form of maths or computer code that is calculating the maths. And you learn something.
So the idea is that a model is a simplified version of something in the real world, which allows you to understand, to test, to predict, to learn. In terms of climate models then, how does one build a climate model and how complicated is it? It's kind of an impossible question to answer, I guess, because different people build them in different ways and there are always arguments around the interpretations and things. But in general, how do you build one?
It's a great question because it really does vary so much. There's an immense variety of models of the climate out there. First of all, we can sort of classify them into two types. There's models that try and reproduce, in some sense, the whole climate, the whole planet all at once. And there are also models that try to just look at one part of it. So I work a lot with computer models that basically only simulate the Antarctic ice sheet. They don't include all of the rest of the world's atmosphere and oceans and everything else. But going back to the big global climate models, so they're perhaps trying to predict the global warming for a given amount of greenhouse gas emissions in the future. If they are more detailed, they might have all the different patterns of that temperature change and rainfall change all around the world. And as I say, the very simplest of those could be just one equation. You can look up, actually, if you're interested, this idea of an energy balance model. And you can get these very simple ones that basically say, we know how much energy is coming in from the sun, and we know how the planet radiates energy in the form of heat because it's warmed by the sun. And there's a balance to those things. If they're out of balance, so if there's more energy coming in from the sun than is being emitted back out to space by the planet, we're then going to accumulate that energy and we're going to heat up. And similarly, the reverse. So in a sense, you can get the basics of global warming and how it depends on things like CO2 in just this very, very simple representation. So that's something I can just teach to my undergraduate students at King's. They can just do it in a spreadsheet or something like this. But then the really, really state-of-the-art complex ones that we use, for example, in the reports of the Intergovernmental Panel on Climate Change, the IPCC, the real state-of-the-art, immensely complicated. I mean, they take decades to build up their complexity. These are models that have been around since the 60s or so, started off in weather modeling and went into climate. They're very related, weather and climate models. And each decade, all this complexity was added, the way that the clouds move, the circulation of the deep ocean, the way that the forests on land and the marine life respond to climate change, for example, through photosynthesis, the carbon cycle, this kind of thing. And you add atmospheric chemistry, so you add sort of things with ozone and pollutants and all of the things we know are in the atmosphere. So decade on decade, you have tens and then eventually hundreds of scientists contributing to these models in this incredible joint effort. Someone like the UK Met Office, their sort of suite of models. I mean, just hundreds of people have contributed to these over the decades. Incredible achievements of science.
The first glacier you ever saw was apparently in summer 2022. Is that right?
That's right.
Now, that surprises me given the nature of your work.
Well, as I said, climate scientists come in all varieties, and I happen to be one of the climate scientists that's relatively remote from the physical reality. So you get lots of climate scientists that use computer models to simulate reality. But actually, although I've done some of that, my work these days is mostly around working with those computer modelers and actually building a second kind of model, if you were really getting meta, a statistical model of their computer models. So basically, I'm doing a lot of data analysis, a lot of synthesis of other people's computer models. So I'm even further removed from having to go out on the ice, for example, if I'm studying glaciers or ice sheets.
Yeah, well, it must be good occasionally to sort of set foot on the thing you've focused on, the real thing.
It's really important for computer modelers and statistical modelers like me to get out and look at the thing that you're studying, of course. But the trouble with studying ice sheets and glaciers in particular is they are quite inaccessible, and it is quite difficult and expensive and so on to get there. You need a certain amount of training. You need to make sure that it's safe. I may get to go possibly to the Andes. We've got a new project studying the Andean glaciers, which had field work. And they did say, actually, they probably could do with having other members of the project who work in the computer modelling helping out with things. So I'm hoping to go again. But yeah, it was wonderful to go to Iceland to see just... You see a glacier from a distance, and that in itself is spectacular enough. Many of us will have seen perhaps a snow-capped mountain, or certainly we can imagine what that's like from pictures or from perhaps a plane. But as you get closer and closer to the glacier, you get more and more of this detail. But most of all, the stories of the people who live there, they say, well, of course, in the 1990s, the glacier was over there. The end of the glacier was, however many tens or hundreds of meters down there. And you really see, for example, these meltwater lakes that form at the end of the glacier where they've been melting. And that lake might have only been there a few decades because it was caused by that extra warming that we've seen in the last few decades. So it's incredibly tangible, particularly for mountain glaciers, to see that loss, basically.
Now, just going back to your work, one of the things that you and your colleagues do, of course, is to predict the future. Of course, I mean, that's how we know about the various scenarios of the future. I wonder how things like emissions, things like human activities play into the models that you've been talking about. We've talked a lot about the sort of physical sort of models of the Earth system and the Earth and the weather and the climate. Of course, it's intertwined with human activity. And I wonder how you model that. And in going towards the future, could you tell me how you create scenarios of different types of policy response, which must be an incredibly difficult thing to model?
Yeah, I mean, I guess the short answer is we don't know what humans are going to do in the future. There's a limit to how much we can try and predict what we will do and make predictions for what we'll do. So the way that we try to tackle that is we use this separate, slightly kind of technical word of projections. So if our emissions are very high, then what would the global warming be? If our emissions are very low, then what would the global warming be? So there's a whole field of people who do that modelling of the impacts of our different possible choices in the future. So whether that's population, whether that's economic growth, whether that's technological change, we're getting more efficient in many ways in energy use. We're, of course, gradually decarbonising our energy by going towards renewables. So all of those things, they get put into, what we call storylines or narratives. We say, if humans do this and if the world evolves in this kind of storyline, then, you put in all the numbers for, I don't know, the coal use sort of decreasing slowly or rapidly, or the offshore wind and the onshore wind and the whatever else. And you put it all in there and you come up with an estimate for the emissions. But there's a sort of limit to how much we try to predict what we will do. It has been emerging more and more, actually. I will say, though, because the whole point about the Paris Agreement of 2015 is that each country or, each party to this, the EU acts as one, they make these pledges for how much emissions will be cut this decade. These are called the nationally determined contributions. So, for example, 68% or 40% or whatever by the end of this decade, which is when the current round lasts. So there is a lot more use of trying to actually predict what the global warming would be if all of those pledges of the Paris Agreement are kept. And there's a great website I always recommend to people called climateactiontracker.org, which keeps track of those national pledges and says, okay, what would the global warming be? You have to sort of work out what would happen after the end of the decade as well, getting to net zero in 2050, that kind of thing. So you still have a bit of flexibility about what might happen in the next few decades. But it's an incredibly powerful way because it means that we can say, for example, if we had been on a trajectory of very high emissions, maybe tripling by the end of the century, which is the kind of highest scenario that we consider, then we predict we'd be heading for about 4.5 degrees of global warming since the pre-industrial. If we implement the current policies, then we'd be heading for about 2.5 to 3 degrees of warming. If we keep to the promises we've made under the Paris Agreement, which are stricter still because we don't yet have all the policies in place to make those pledges happen, then we're heading for perhaps just under 2 degrees of warming. So just starting to match the upper limit of the Paris Agreement, which said we'd keep to well below 2 degrees of warming. And then what we want to do is be even more ambitious and make those promises better, those pledges under the Paris Agreement better, those net zero pledges for the middle of the century, and try and keep as close as we can to limit warming to 1.5 degrees.
So, I mean, that's kind of like a stark warning, isn't it, about the kinds of things that can happen if under different scenarios. What do you tell people about how confident you are about the predictions you're making? Because they are predictions that you don't say this is going to actually happen. They're all probabilities, they're possibilities of things happening. How do you persuade people about the fact that there are errors in these things, there are mistakes, there are possibilities and probabilities that we need to think about, but we need to take them seriously?
Yeah, I mean, I think broadly speaking, we've got a good majority on people agreeing with the idea that we are going to see more global warming because we know that carbon dioxide has this warming effect. And because when you warm a body of water, like our oceans, they expand, that means we also know that sea levels are going to go up. And both of those things are certain, certainly over the scale of the next few decades, I would say for temperature, it's pretty hard to avoid any more warming from now. We're going to see some more warming. And sea level rise will be slow to come back down. It will basically stay higher for hundreds, if not thousands of years. So those are two certainties. And there aren't too many people who are completely unconvinced that we're having any impact, I think, on the climate. But I do think it's important then when people are either unconvinced or confused, and both of those can come from the same thing, which is that you do see quite a lot of different predictions in the news. And not that everyone's kind of trying to keep track with a spreadsheet of, well, these people said it was going to be 63 centimetres of sea level rise and these people said it was 42. I'm not saying that, but there's a sense of, yet another prediction, and haven't we heard this before, and why are they coming up with a new number, and why is this one saying it's better than we thought and this one saying it's worse than we thought. And I think my sort of career, if you like, in science communication has been around trying to get across why that is, I guess, why scientists come up with different numbers and why those numbers change over time. And it's really because of two things, I think. Science is a process. It's something that's constantly evolving through time. We constantly learn and improve. We're very happy to do a U-turn if we find out some new information that means we were wrong before. So there's that side, and the fact that different scientists are looking at the problem in different ways as well. They have different models, they have different assumptions.
Hello, I'm Camilla Nichol, Chief Executive of the UK Antarctic Heritage Trust. We work to preserve and protect Antarctica's unique heritage, from the historic huts of early pioneers to the amazing discoveries in climate science. Our mission is to inspire current and future generations to discover, value and protect this precious wilderness. Every year, our specialist conservation teams head south to Antarctica to conserve and protect our historic huts. With your generosity, we can preserve these amazing sites and bring to life the many fascinating stories they have to tell. Find out how you can help save Antarctica, protect our planet, and even adopt a penguin at ukaht.org, or search for the UK Antarctic Heritage Trust. Thank you. Enjoy the rest of the show.
Antarctica, the coldest, driest and windiest place on Earth, where the penguins outnumber the people, there are only 2 seasons and no time zones. Discover this vast, breathtaking, frozen continent on a Hurtigruten Expeditions cruise. It's an adventure like no other. Explore the landscape, get closer to nature, and learn more than you'd expect with our knowledgeable Hurtigruten Expeditions team. Search Follow Your Curiosity to book now.
How important is Antarctica in understanding sort of the direction of climate change in our planet? You wrote on your blog recently a post which was kind of like a foreshadowing of a tragedy almost, which is called Things We Take for Granted. And it's all about a part of Antarctica that perhaps people don't really take much attention to, but you did, and you found some problems. And this is the east of the Antarctic rather than the west, where a lot of the sort of visits and a lot of the expeditions go. Tell me about that. What's happening in the east of Antarctica? And generally speaking, what is Antarctica in terms of trying to understand the future of the climate?
Well, I can say quite simply why Antarctica is so important, because sea level rise is one of the biggest challenges of climate change, one of the most difficult impacts of climate change to adapt to, the increase in coastal flooding that it brings about. And Antarctica is the most uncertain part of future sea level rise. We don't have a very good understanding at the moment of whether it will be a small contribution, particularly over the next 100 years or so, or a very big and accelerating contribution, which really completely changes the picture and absolutely dominates everything in sea level rise. It's a real wild card. And a big part of that story is West Antarctica, which has been much better studied. That's because that's where the changes are happening now. We're seeing the most ice being lost because of warm ocean waters, in particular, in one part of West Antarctica. And East Antarctica is much bigger, but it's also much colder. The air temperature is very, very cold. We need these records set in Vostok and so on. And the water surrounding East Antarctica is cold. And so, the kind of cliched metaphor is that we think of it as this sleeping giant. We don't think that it's too easy to disturb because it's been there for so long. The West Antarctic part has kind of waxed and waned over tens of thousands and millions of years. We know that it's come and gone over time, and that's why we know that it's quite vulnerable today. But East Antarctica has been much more stable. And I think the thing that we tried to highlight in that review is that there is a possibility for change there. We do see ice being lost in a particular area called Totten Glacier, which is looking worrying. It's got the same kind of signature, actually, as West Antarctica. There's a bit of warmer ocean water there. It's just, we know less about it, and that in itself, the uncertainty in itself is difficult. But also that if warming were to be very high, and particularly if the ice sheet seems to be at the most sensitive end of our predictions, then there's just so much ice locked up there in East Antarctica that really it starts to make very big changes, especially over sort of several hundred years to thousands of years. And that's not obviously a timescale that people particularly think about for their daily lives, but clearly the implications of setting off, potentially irreversible changes that could lead to many meters of sea level rise that really change coastlines around the world.
I wonder in what other ways Antarctica matters to your profession. You talk about making sure that the models that you build for the future are grounded in reality. How far back does that data collection go, though? I mean, I think about the heroic age of Antarctic exploration, when scientists and explorers were going off to find this place and map it and take measurements of the magnetic fields and temperatures and wind speeds and all of that. Does any of that data that was collected 100 years ago by these epic explorers, does any of that figure into the kind of current sort of very cutting edge climate models, or is that historic and no one uses it?
Well, certainly we scientists are always trying to dig around for whatever data we can, or whatever kind of record, even diaries and, observations from ships that have traveled around the world over the last few hundred years. Any kind of expedition, any kind of observation doesn't have to be even a measurement. It could be, seeing sea ice or not seeing sea ice at a particular time of year, this kind of thing. So we certainly try to use everything. I mean, some examples are more about scientists going out and drilling, for example, into the sediment around Antarctica, or drilling ice cores from Antarctica. Those both give us information about, so the sediment will give us the kind of rock and the mud and silt and so on at the bottom and around Antarctica will tell us a history of weather, of when there was ice in that part of the world and when there wasn't. So therefore, whether that part of the ice sheet has retreated or expanded at different times in the past. And then the ice cores will give us an idea of things like how the snowfall has changed. Because of course, if you get more snow falling on Antarctica, which can happen in a warmer climate, sort of unexpectedly perhaps, it actually counteracts some of sea level rise because it's going to build up the ice sheet a bit. And as well, ice cores have been used to reconstruct the temperatures over Antarctica. So certainly, everything from the scientists' expeditions through to the more kind of colonial explorations, if you like, of, sailors in the British Empire or anyone that's basically observed anything. There are incredible projects to gather that together. Citizen science projects. Old Weather is one of the big ones that's been around for a long time, where people can go and actually look at these ships' logbooks and then type in the weather measurements into the web tool, and actually that gets used and gathered by scientists. So we're constantly trying to scavenge data that goes back. But I think most of the data that I use does tend to come from the satellite records because they're much more complete. That just tends to go back for Antarctica. The main record that's kind of most complete goes back to about 1992. But the earlier information is really useful because the ice sheets change on long timescales. The further back in time we go, the more we can understand about the long-term response to change, how much of today's change is natural variability compared with how much of it is caused by humans. I had a PhD student finish recently, Jamie O'Neill. He was testing an Antarctic ice sheet model with data reconstructions of how Antarctica looked 3 million years ago in the mid-Pliocene warm period, sort of 3-4 or so degrees warmer than today. And that was based on data of the sort of sediments and rocks, erosion sort of signatures of marine life showing that a bit of the planet used to be, ocean rather than land. Debris from icebergs that has been carried over the oceans. These are all things that are used to try and infer where the boundaries of the Antarctic ice sheet were even 3 million years ago, and then use that even to test ice sheet models so that you can have more confidence in their predictions for the future. Yeah.
You've been a very powerful voice on how all of us can take action on climate change. And I just wonder, for somebody who's been talking about this for a long time, patiently explaining what's going on for a long time, having to deal with people who are disingenuous in their responses and still being patient and calm about it all. I just wonder how you think the world is doing. We've just recently finished another round of COP meetings. Progress seems to be happening slowly, inching forward. Who knows? It's hard to tell. How do you think that the world is doing on this front in terms of just addressing, tackling, dealing with climate change?
I'd start by perhaps saying that you mentioned people kind of being disingenuous. I think people always have their reasons for saying what they say. I think if someone is unconvinced on climate change or obstructive in some sense, or, I don't know, teasing me on Twitter or whatever else it is, they have their reasons, and whatever they are, I think it's just important to try and understand those. And that comes to the politicians and the business leaders and so on as well, who have to actually make tough decisions, that are costing money in the short term, even if they save money in the long term, who are trying to work out what's popular if they're someone that's voted in, if they're trying to work out how to be a good leader. In terms of the progress that we're making, well, it's better than it could be, and it's not as good as it should be. It's really,
that's the best you can say, anyone can say, isn't it?
Yeah, I think one thing I try to push back on, though, is the idea that nothing is happening at all. We are making progress, and some of it is intentional, like policies put in place for climate change, reduction in emissions. Some of it is unintentional in the sense that we're just decarbonizing, improving our efficiency and so on. But we are making progress, and it's much more important to acknowledge, I think, where that progress is being made and where it needs to speed up and where it needs to be scaled up and where it needs to be more considerate of environmental impacts, rather than kind of get into a rut of thinking nothing is happening, nobody understands, everybody's an idiot, we're all doomed. It's not correct to think that way, because there is a kind of momentum, and it is partly through people wanting change, and it's partly through others actually thinking, well, change is inevitable. Businesses, for example, they don't want to get left behind. If they think, well, decarbonisation is coming and regulation is coming, they don't want to be dinosaurs. They don't want to be behind the curve. So there's a kind of momentum happening, and who knows if it will speed up quickly enough to limit warming to the levels that we want it to. But it's always a continuous process of improving those promises and pledges and technologies, because this is a story that's going to play out the rest of the century. Right? This isn't something that we do this year or in the next 5 years or the next 10 years. It's something we keep doing.
Yeah. Do you think it's ever going to be possible to reverse any of the impacts that we're seeing from climate change, or that we will see? I mean, is the world irrevocably changed at this point? And how much of that change might we wrest back?
There are definitely some parts of climate change we think could be reversed and others that couldn't. So the kinds of things that could, in theory, go back to, pre-industrial, before we've had the 1.1 degrees of warming we've seen so far, things like the changes in weather, the heat waves and so on, if we could get temperatures back to pre-industrial levels by extracting CO2 from the air, and it would sort of gradually happen naturally anyway over a long period of time, then things like extreme weather, changes to the Arctic sea ice, we think those things are reversible. Where things aren't probably reversible are the areas that I work in, the glaciers, the ice sheets, basically the frozen parts of the planet, anything where it takes a very long time to build up the ice or to build up something like the carbon in peatlands and permafrost, the sort of permanently frozen boggy lands of the north. It's a lot faster to melt ice and to thaw permafrost than it is to regain that ice sheet or to restore the peatlands, for example, that you lose. So, for example, if we have triggered changes in West Antarctica that are irreversible, which we basically don't know if we have or not. We think we might have done, we're not sure. Even the fact we think it's a possibility is obviously terrible. That's something that once you lose that ice, once you get that sea level rise, it just takes thousands of years to come back. That's not any kind of human timescale we can imagine. So it's effectively irreversible. So things like sea level rise, ocean warming are things that take a really, really long time to reverse and effectively are irreversible.
I know that you've not got any current plans to go to Antarctica, but for when you do go, if you could only take one thing with you, what would it be?
Oh, I haven't thought about this. What would I take? I must say I have a mixed relationship with the cold. So apart from the hot water bottle, I think it's got to be a photo of loved ones, hasn't it? Because if you were going on a scientific expedition or if you were being sent by virtue of a podcast on your own into the middle of Antarctica, you'd want to be sharing it with someone. You'd want to perhaps write someone a letter while thinking of them. So as I speak, maybe it would just be the notepad to write about it so that I could send the letter home about how it was to be in Antarctica.
And a final question, why does Antarctica matter to you?
There's nothing like it on Earth. It's the most enormous, beautiful, unique, cold, white, unpredictable, important part of the planet, I think.
Tamsin, thank you very much for your time.
Thank you so much.
Thank you very much for listening. A Voyage to Antarctica is brought to you by the UK Antarctic Heritage Trust and made possible by support from Hurtigruten Expeditions. To find out more about our guests and how you can support the Trust, please head to our website www.ukaht.org or to our Facebook, Twitter and Instagram pages. If you enjoyed this episode, please don't forget to follow and rate us wherever you get your podcasts. It makes a huge difference to us. Next time, I'll be talking to award-winning architect Hugh Broughton to find out what it takes to design buildings where people can live and even thrive in the world's most extreme conditions. This podcast is part of the Trust's Antarctica in Sight programme, supported by the Foreign Commonwealth and Development Office and charitable gifts and donations. A Voyage to Antarctica was presented by me, Alok Jha. Music is by Alec Hughes and editing by James Stickland. The show is produced by Jessica Norman. See you next time.